Recording. Okay. Good afternoon, guys. Today, we're going to continue our lesson. So, recap lang from last time. Yung ginawa natin last time. So, basically, we have started magnetostatics. Okay. Sa magnetostatics, inalam natin yung forces due to magnetic fields. Yan. And then, what causes magnetic fields? Currents. So, discuss natin yung mga current. Okay. And the force that is due to a current. Alright? Okay. So, yan. Then, we pahapyaw, kinuha natin yung continuity equation. Then, of course, we proceeded. Yung word bang ganun? Okay, basta nag-proceed tayo. Proceed tayo sa getting magnetic fields kasi ayun yung kailangan natin, di ba? Okay? Proceed tayo doon through Biot-Savart law. Okay? So, ayun yung mahirap na integral. Okay. So, recall lang natin na yung magnetic field mo would always be perpendicular to the current and to the separation vector. Okay. So, hindi niya pwede maging kaparallel yung dalawang yun. Kasi cross product siya ng dalawang yun. Okay. Okay. Then, nag-example tayo. Nakuha natin na yung magnetic field, the distance S from a long straight wire is given by B is equal to mu naught I over 2 pi S. Tapos, yung direction niya would be phi hat. Okay? Okay. And then, these are the other forms of the magnetic field kapag given ka ng surface current K at volume current J. And then, sinimulan na rin natin yung divergence and curl of magnetic fields kasi, di ba, parang sa electric field lang, kinuha rin natin yung divergence and curl. Okay? So, baka may makuha kasi tayong easier way to do this. Alright? So, una, ginawa natin na yung del dot B equal 0 yun. Yung divergence ng magnetic field, 0 siya. And then yung curl, may nakuha tayong value, which is yung del cross B is equal to mu naught J. Okay? Okay. And then, doon na tayo na-stop. So, tuloy natin, no? What can we get from here? Okay? Ayan. So, Ampere's law. Balik tayo dun sa result natin na del cross B. The curl of B is just mu naught J. Okay, so J yung ano natin, no? Kung naalala natin yung volume current. Okay? And then, what arises from this is, gusto ko ipa-bonus prob set eh. Iniisip ko pa kung paano yung proof nito. Okay? So, basically, if you're gonna follow the instructions of the derivations of this in your book, kung naalala natin, okay. Oops. Kung naalala nyo, okay, di pala ito yung papaprod set. Mali. Okay, anyway, kunin natin yung Stokes theorem. No? Baka may makuha tayo pala tayong okay, so Stokes theorem natin ng dalawang to by integrating. Okay, integrate natin siya over some area, dA. Joke. Let's get the dot product. Okay. And then, With this is just equal to your mu naught J, tapos in J dot dA ito, di ba? Mu naught J dotted with dA. Okay? Okay. Imagine natin itong J dot dA. So, suppose you have some area, hindi siya closed, no? So, we can say na kaya meron kang circular area. Okay? So, this is your PA. And then, meron kang something there na current. Okay, kuwari ayun yung current mo. Parang tubig lang. Okay, so what is this J.dA? So J.dA would be counting the lines that pass through in this area. Okay, so yung J.dA, minimeasure nyo lang kung gano'ng karami pumapasok dito sa area na to. Okay, and what does that mean? Yung J.dA mo, this is just color. It has a blue. This would just be the current that you are feeling in that area. Okay? Okay? So that is ayun yung total current na napi-feel mo dun sa area na yan. Okay, so that's your J.TA. Okay, now balik tayo sa left-hand side, which is this guy. So Stokes theorem, anong mangyayari dyan is that this is actually equal to the closed integral of B dotted with PL. Okay? And kunin natin yung right-hand side, which is yung mu naught I enclosed. We have this. Okay, we have mu naught I enclosed. Okay, so ayan yun, di ba? Alright, what does this give us? Now, if you know that, di ba, nung sa Gauss's law, Gauss's E.dA, Q enclosed over epsilon naught. There are two things you need to know, which is yung closed and enclosed charges mo. Then you have to make sure that E.dA is yung electric field mo dapat perpendicular siya sa area or parallel siya to the area vector para maging E times A na lang ito. Okay? Okay. With that, dito naman, i-ensure natin, emotional assurance. Okay, i-ensure natin na B has to be always parallel with the path of the current. With the path B at BL. Dapat yung magnetic field mo, dapat nagra-run through siya dun sa iisipin mo path, sa loop. Loop siya kasi, enclosed siya. Okay, ang tawag doon ay Amperian loop. Amperian loop. So last time, Gaussian surface yung ano natin. Okay, Gaussian surface. So this time, Amperian loop. So let's try. Try natin yung example para hindi tayo medyo lost. Okay? Okay, so find the magnetic field at distance S from a long straight wire. Kung naalala nyo to, binasa ko to kanina, di ba? So hanapin daw natin yung field at distance S from a long straight wire. So this is it. Okay? Okay. How do you know that ano yung DL mo? Okay, so iisipin mo ngayon kung saan nagpo-point yung magnetic field mo. Okay, this is parang ito yung pinakamahirap na part dito, pero ayun na lang iisipin mo. Basically, you know that you know that yung current mo, magpo-produce siya ng magnetic field that circles around it. Okay? Tapos susundan mo na lang yung right-hand rule. So, nag-circle dyan yung magnetic field mo. Okay? So, with that, alam mo nag-circle yung magnetic field mo around the current. So, you have to pick that circle, so that buo yung makukuha mong B.dl. Okay? So, I have B.dl. Alam ko na circle yung path ng magnetic field ko, so I know B times the circle. Kung gaano kahaba yung circle, that would be 2 pi s. So, ayan, Amperian loop yung Amperian loop mo. Kasi alam mo na yung loop na ito, kaparallel niya yung magnetic field. So, parallel. Kahit hindi sila straight lines. Okay? Tapos, you know that mu naught I enclosed. So, what is your I enclosed? Titingnan mo lang kung ano yung I na pumapasok dun sa loop mo. Okay? Sa loop mo may pumapasok na this much, which is yung I itself. So, mu naught I. Okay? And then, you know B, divide mo na lang. Amazing! Ngayon din yung sinolve natin last time. Wala tayong integration na ginawa or anything. Okay? So, you just have to know kung paano siya, yung direction niya. So, that would be C hat. Okay? Assuming na ito this is Z hat and this is S hat. Kung ayan yung cylindrical coordinate na gagamitin mo. Okay? Okay. So, pwede mo balibalik ta rin yung, balibalik ta rin yung coordinate system mo. Sir, paano po ulit yung I enclosed? The I enclosed would be the current that is passing through your loop. Okay? So, may loop ka. Titingnan mo lang, bibilangin mo lang kung ano yung mga pumapasok na current sa'yo. May loop ka. Ano yung pumapasok sa butas na yun? And then, yung pumapasok doon will just be I, yung wire mo. So, yun lang. Okay? Ang problema ngayon, paano kung may mga problem na ganito? Kuwari, makapal yung wire mo. So, maraming pumapasok na wire. Maraming current. Okay? May dumadali na marami. So, iba yung paano pag nag-Amperian loop ka sa labas, nag-Amperian loop ka sa loob, ano makukuha mo. So, nasa, nagpapaprobset ako syempre pag ganun. Okay? Parang yung sa kung makikita niyo analogy nito would be kuwari meron kang spherical charge, solid spherical charges. Okay? Tapos uniform yung distribution niya. And then, so pag kinuha mo yung Gauss's law dito, diba, E.dA. Pag nasa labas ka, madali lang. E, tapos yung 4 pi r squared must be equal to 4 pi r squared must be equal to the total Q. Kasi nasa labas ka na, di ba? So, madali lang yung electric field nito. Total. Ginawa niya ito sa problem na alala niyo. So, lang not r squared. So, this r hat. Easy. Tapos yung nasa loob yung problema. Kasi a portion lang ng Q yung makukuha mo. So, parang ganun lang din dito. Pag kumapal na yung current mo. Dito kasi madali lang kasi single line lang siya. Okay? Okay. So, tuloy tayo. Another example. Siyempre, kung may line, may surface naman. Okay. Find the magnetic field of an infinite uniform surface current, which is yung K natin. Okay. Na nakatutok sa x hat. Okay. So, ito yung image niya. So, may XY, nasa XY plane, may nag-flow na K towards x hat. Okay? So, first things first, imaginein natin yung magnetic field natin. Okay? So, let's say, gawin kong pula yung blue na lang tayo. Hindi, sige, green. Kuwari ay yung current. Oops. Sige, kaya ko to. Kuwari straight line yan, guys. Okay. Kuwari ay yung x hat. Okay? Tapos, the magnetic field would of course be followed by the right-hand rule. So, tama. Okay. Right-hand rule lang. Imagine natin, kuwari may tatlo ka lang. Okay. Tingnan maigi, tingnan maigi. Okay, nagtatanong ako. Si Jello. Are you there, Jello?
Yes po, sir.
Ayan. Okay. At this point, by superposition, ano yung mararamdaman mo magnetic field dito? At this point. At this point.
Wait lang po.
Pa- Gawin natin yung ano. Wait lang, gawin ko muna yung front view ng X. Kuwari, ito yung harap ng mga arrows. Okay, kuwari nandito tayo. Kuwari nandito. Nakatingin tayo dito. Okay. Kuwari nakatingin tayo dyan. Tingnan natin yung front view ng arrows. Makikita mo by the right-hand rule na magnetic field mo would be circling. Okay? Circling. Okay. Okay, now, Jello. What do you think is the magnetic field right here? So, by superposition, kung anong nadadagdag nito tsaka ito. Huwag mo na pansinin itong pangatlo. Sige.
0 po, sir.
Yes, very good, 0. So, between these points, nagka-cancel lang sila, no? Galing, 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 galing. Thank you sa sagot, Jello. Okay. So, at these points, 0 lang sila. Wala silang nagka-cancel lang yung mga yan. And since yung system natin is infinite uniform surface current, so imagine this as tuloy-tuloy lang siya. So tuloy-tuloy lang itong tuloy-tuloy lang yung current mo. So in essence, ang mabubuhay lang na field is yung nasa taas. Okay? Nasa baba. Okay. So in essence, ang magiging itsura ng magnetic field mo, kuwari ito yung tinitignan natin yung nakatutok sa atin yung x-hat, yung current nakatutok sa atin. So yung field mo, the magnetic field would be something like this. Okay? Okay. So ganyan. Extending to infinity, of course. So ang kailangan lang natin is some portion of it. Okay? So, pipili tayo ngayon ng Amperian loop na madadaanan tong mga magnetic field mo. Okay? So, we can say that our Amperian loop would be something like this. Pili ako ng some square lang dito. Okay? So, gagaanan natin to. Okay? Upward. Then going here. Here. Okay? Pag ganyan yung loop ko. So, in 3D, kung mas magugusto nyo yung 3D, ito yung loop mo. Okay? Okay. Lipet. Now, what do we do? Set up mo na equation mo. So, B.dl, B times, sabihin natin length L ito, no? This would be some length L. Arbitrary na lang para pwede natin siya extend to infinity if we want. So, alin nyo may mga field lines? This would be yung top and bottom parts. So, how long is that? 2L. Tama? Times 2L. Okay? And then, that must be equal to mu naught I enclosed. Okay? So, ang point natin, hanapin natin ngayon yung enclosed current. Ano yung enclosed current? So, yung mga current na dumadaan sa atin, papunta sa atin. So, this part lang. So, what is this current? So, that would be, alam natin na ito ay K. Alam natin na sila ay K times L. Okay? K times L. Naniniwala ba sa atin? Naniniwala ba kayo sa akin? Nawala yung sinishare ko. Joke, ito pala. Okay? Paano po nangyari yun, sir? Yes, very good question. Okay, ano yung K natin? What would be K? Paano natin dinefine yung K last time? Tayo. Natin definition ng K para systematic tayo. Okay, similes. Okay, sige. Meron kang nag-flow na K. Meron kang nag-flow na K, di ba? So, at any point, makukuha mo si value ng K. Tama ba? Kasi si K ay, surface current density. So, this is current density. Density. Okay? So, pangalanan muna natin, surface current density. Okay, now, ano ibig sabihin ng surface current density? So, the total current, I thought, would be K times total area. Tama? Kasi si K ay surface density, so if minultiplyan mo siya ng surface na area, that would give you the total current in an area. Okay, so suppose that we have your area, let's say this is green, itong green na ito ay yung area mo. Okay. So to know the whole current that is flowing, para ito ay length, ito ay with, if you're given a K, then you know that your total current is given by K times width times length. Now, if you're going to just pick out a strip, kukuha ka lang ng isang dimension. Tama ba? Gets na ba? Intuitive na ba? So if you're just gonna get this part, yung blue mo, that would mean that I would just need to get yung length na kinuha ko times K. Okay, kaya ayun lang yung kinuha nating amount of K. Okay? Okay? So B would be equal to mu naught KL divided by 2L. Oops, nawala yung susulat. So, mu naught K over 2. Now, what is the direction? That could be going to this, going to the left, or going to the right. What is left here is, so y hat yung direction mo, okay? Y hat yung direction mo, it can be negative y hat, or it can be positive y hat. So what is the boundary? Yung boundary mo would be, if it is above the xy plane, so mu naught K over 2, then the direction would be negative y hat. If it is above z, so for z greater than 0, and then mu naught K over 2 y hat if it is z less than 0. Okay? Amazing. Okay? Any question? Kukuha pa ba? So, ayan. Okay, so nakadalawang example na tayo. So, medyo, medyo iisipin mo pa dapat kung paano umiikot yung mga magnetic field mo bago ka makapag-proceed sa Ampere's law. Kasi pag nagkamali ka ng Amperian loop, magkakamali-mali yung sagot mo. Okay? Okay, let's try another example, syempre, para hindi naman tayo lost. Kasi kailangan madali yung mag-gets mo Ampere's law. Okay? Okay, so let's now try to find the magnetic field of a very, very long solenoid consisting of n closely wound turns per unit length on a cylinder of radius r, each carrying a steady current I. Okay. So, sinulat niya yung closely wound turns per unit length is that para maging, pwede natin assume na circular yung each turn. Kasi di ba pag inisip magiging helix siya, di ba? Magiging helical yung, pag hindi siya closely wound, magiging spiral siya. Hindi pala helical lang. So, magiging spiral. Magiging spiral siya. So, if you are going to make it very close to each other, so, ang mangyari, yung each turn mo, magiging circular na siya. Okay? So, bale, multiply mo na lang yung circle by the number n. Ayun yung ganun karaming circles na yun. Okay. So, kung hindi raw tayo komportable doon, nagbigay si Griffiths ng ibang way para isolve ito. Ayan. Sinabi niya na pwedeng sheet of aluminum foil na lang, tapos nagbibigay ka ng surface current, Ni. Ayan. So, pero kasi in essence daw, yung field inside a solenoid is huge. Tapos, compared siya dun sa longitudinal current. Okay? Kasi pag spiral yung spiral. Yung setup mo, mayroon kang longitudinal current. Okay? Pero ayun ay very relatively small daw compared to your field that is inside the solenoid. So what is a solenoid? So yung solenoid ay basically may tube ka na something or kahit hindi hollow, basta may cylindrical object ka, binalot mo ngayon sa wire. Okay? So ito yung itsura ng solenoid. So may umiikot na current sa cylindrical object. Okay, in essence, pwede mo nga rin daw siyang isipin na yung cylindrical object kung binalutan mo ng aluminum foil, tapos pinadaan mo yung K like this. Okay? Okay. Okay, so how do we do this? Okay, there are two regions na pwede nating i-observe. Okay? So sabi ko nga kanina, nagsisircle lang yung magnetic field mo sa mga current mo. Okay? So if we're gonna do the right-hand rule here, mas madali mag right-hand rule dito. So, pag ganun yung current, ay yung magnetic field mo. Okay? Okay? So, pag paikot, pero sabi nga ni Jello, nagka-cancel itong mga to. So, in essence, pababa lang yung magnetic field mo. Then, sa loob pa, taas. Okay? Okay. Alright. So, pwede tayo mag-isip ng loop na pwede natin red yung loop natin. Pa-square ulit. Tapos, up sa loob, pataas, sa labas, pababa. So that, kasabay na yung magnetic field. Okay? And then, we can still have another loop here para malaman natin yung field outside. Okay? Okay? Bakit natin to pwedeng gawin? Kasi, yung etong part na to, pwede siyang may component galing sa ditong part. So, etong part na to, meron siyang magnetic field pupunta dito. And then the other parts would constitute the magnetic field there. So, let's see. No? Tingnan natin muna kung ano mangyayari. Okay? Okay, so let's denote this loop as loop number 1 and loop number 2. Alright. So, sa loop number 1, okay. Mag-denote muna ako ng axis ko. So, I say this is Z. Tapos ito ay S hat. Okay. Kasi may cylindrical symmetry ako. So, baka madaling gamitin yung cylindrical coordinates. Alright, so si loop number 1, okay. First things first, isipin muna natin kung anong direction yung B. Kung naaalala nyo, si B, dapat mayroon siyang component. Sa Biot-Savart law, dapat siya ay I cross the curly R hat. So, bawal siyang maging ka-direction ng current mo. So, yung current ay phi hat direction. So bawal na agad si B maging phi hat. And then si R ko ay tinitingnan ko siya with respect to the with respect to the z-axis. So S yung magnetic field ko, diba? So bawal siya maging S hat at phi hat agad. Okay, kasi may cross product pa dun pagdating sa Biot-Savart. Sir, pa-clarify po ko saan nakaposition yung yung loop number 1. So, sabihin natin yung position ng loop number 1 ay some distance A, some distance B. Okay? Okay. So, sa loop number 1, B, that DL ko, yung DL ko ay wait lang, double check ko lang ang aking sagot. So, tapos sabihin natin may length ito na as usual, ito ay, oops, what am I doing? This is L, okay? Okay, now, my field is not uniform, so iba yung field sa A, iba yung field sa B. So, denote lang muna natin sila as BA at BB. Okay? So, yung una ko ay B. Oops, ba't nangyari? Sorry. Ayaw na magpalit ng color, guys. Alam ko na ito ay BL, tapos mu naught. Ano yung current enclosed dito? Wala, di ba? Kasi wala naman nagpa-pass through na wire dito. So, 0 ito. I enclosed equals 0. Then, I know B has two different magnitudes. So, kunin ko yung BA ko tsaka BB. A minus B. Okay? Times L must be equal to 0. Okay. Yung direction ay yung signs nito ay depende lang sa direction. So, yung BA ko ay pataas, so positive. Tapos yung BB ko ay negative kasi pababa. Tapos times L, which is yung prescription ng Ampere's law. Then, on the right-hand side, dapat 0 yung enclosed current ko. Kasi wala namang current dun sa loob ng loop number 1. Okay? So, what does this mean? Is that yung BA ko should be equal to B. Okay. Now, what do we know about this info? Okay. Like electrostatics and magnetostatics, nagbavanish yung magnetic field mo at very far distance. So let's look at the Biot-Savart law. Yan guys, nagluloko yung ano ka. Yeah, sorry. Let's look at the Biot-Savart law. Kailangan ko kayo makonvince na mag-vanish siya at infinity. Okay? So, makikita nyo dito, yung R mo is R squared. So, at infinity, mag-vanish yan, of course. So, that gives me something here. So, if I pick B to be very far from the origin, then I could say that if B is extending to infinity, this is the 0, therefore, yung malapit lang din sa kanya, mag-0 lang din kasi, di ba? With this equality, with this expression. Okay? So outside the solenoid, the field is just 0. Okay? Okay. Now, let's use loop number 2 to find out what's inside. All right. Okay. So again, we have two fields. So B in minus B out. Tama? Times yung length ko. Okay, sabihin natin L pa rin siya. Hopeful naman tayo na magka-cancel din. Okay? And then mu naught I enclosed. Now, what is I enclosed? The I enclosed would be the number of wires that is enclosed in this loop. Okay, sabi niya, N per unit length of a cylinder. Radius R, carrying a steady current I. Okay. So N per unit length. So there is number N per unit L. Okay? So this would be N times L times I. Okay, paano nangyari yun? N is turns per L. Tapos, multiplyan mo ng L. Okay, so if I multiply this by yung NL mo would be, mali pala connotation, curly L pala yung ginawa ko. Okay, so curly L. NL would be the number of turns. Okay? Okay? So, point lang naman is mabilang natin yung number nung nakalusot na wires. Okay? So, kung ilang turns yun. And then per turn, may isang current. So, multiply mo ng current. Tama ba? So, nakuha natin yung NLI. L ito. Sorry. Ibang notation. And then we know that the B outside is just 0. So, B inside times L. So, we have our magnetic field inside the cancel lang L. Inside the solenoid to be B is equal to mu naught Ni. Okay, buni. Mukha siyang buni. Buni. Aha. Okay. Wala lang. Mga palatandaan lang. Okay? So inside the solenoid, the magnetic field would point upwards. Z hat. According to my coordinate system. Okay? Alright. Okay, may tanong ba? May tanong? Sir, paano po ulit na 0 yung B outside? Okay. Balik tayo dito, no? So, ginawa natin yung Ampere's law. Then, we found out that outside, wala kang ma-enclose na current. So, that gives me 0 on the right-hand side. Now, there would be, in-assume natin that the magnetic field nearby would be different from the B from farther. Okay, so B, A minus B, B. Okay. So, yung signs lang kaya minus yan kasi pababa yung isa pataas. Okay? So, with this, okay, kung divide yung L, no, mawawala lang yung L dahil sa 0. And then, this expression tells me that the magnetic field at some point nearer to the solenoid would be equal to the points farther to the solenoid. Okay? So that means if I vary B, kung ano man siya, kung pwede siya malapit or malayo, pwede yan malapit at malayo, and we know that B vanishes at infinity. Okay? So, at infinity, equal lang din yun sa malapit. Okay? So, B is equal to actually, di ba? B is equal to A. Pwede, equal din yan sa B is equal to A plus 1. Equal yan din siya sa B is equal to A plus 2. Equal lang din siya hanggang makaabot ka sa infinity. Infinity. Kaya siya nag-zero out. Okay. Kasi kung hindi zero si BA, kuwari BA is some constant, pero sinasabi mo na si BA ay equal sa BB, okay, sample. And then, kuwari si BI nag-extend to infinity, pero si B at infinity, alam mo, by Biot-Savart law, zero yan dapat. So, C, that constant, should be equal to zero. Kuha na ba? Nakuha ba? Nagets ba? Nagets? Okay, thank you. Okay. Ang galing, di ba? Ang dali gumamit ng ang dali nito. Kung gusto niyo tumakas muna sa integrals, syempre pupunta ka sa Ampere's law. Titignan mo ngayon kung may makukuha kang magnetic field through Ampere's law. Amaze. Okay. Guys, yung Gauss's law, for lang yan, electric field. Yung Ampere's law, for magnetic field lang. Okay? So, hindi nyo pwede gamitin yung Gauss's law sa potential. Okay? And yung Ampere's law kung saan man. Okay? Okay. So, we have that, no? And we go back. Let's take a step back. Tingnan natin kung ano yung meron sa mga na-discuss natin dati. Okay? So, electrostatics and magnetostatics. Tingnan natin yung equations natin. Alam natin that the divergence of E is just rho over epsilon naught. Okay? So, you use the divergence theorem here. Divergence theorem. Para ma-produce mo yung E dot dA must be equal to Q enclosed over epsilon naught. Okay? Sir, follow-up lang po. Applicable po ba yung B out z equal to 0 sa ibang system? Is this applicable? I can't say for sure. Hindi ko ma-generalize. It might be not that case. Hindi ko siya ma-generalize. Okay. So, ang tanong ay, pwede ba i-gamitin itong B out? Kasi yung i-result natin na B outside would be 0. Is that applicable in general? Depends on your system eh. Pero for solenoids, yes. Kasi pare-parehas lang silang solenoid. One thing to think about is that if you're gonna make an Amperian loop right here, you know that the field is going up inside, going down outside, and you make another Amperian loop here. You see that it goes upward inside, downward outside. And if you extend this loop, into a much bigger loop, you will see that downward pa rin to. Downward pa rin yan. And then on the right hand side, upward na siya. Okay? So ito ay downward, ito ay upward. So pag tinignan nyo yung ganitong system, probably mag-zero at itong dalawang to. Okay. Pero I could not, hindi ko ma-ensure na ganun lagi. Okay, it's just my way of thinking. Baka probably zero sa labas. Pero make sure ko pa rin. Okay, so ito yung ginagawa ko nung dati kong mga try sa electromag. Okay. Pag feel ko na mag-zero out sila, I just have to ensure that. Okay. So ito yung way ko to imagine kung mag-zero ba sila o hindi. Kasi kung nangyayari to, parang in my experience, they would always zero out. Zero out outside. Pag ganyan yung nagko-coincide yung mga Amperian loop. Okay? Sa inside kasi, titingnan nyo, kahit anong loop gawin mo, makukuha mo na upward inside yan. Kaya hindi siya nag-vanish inside. Okay? So, you have to make sure. Ayun yung point. Okay, now we go back. Sa electrostatics, kinuha natin yung divergence and curl. And from the divergence, nakita natin na may value. Okay, and then we do the divergence theorem, and we found out that we can have this. And this is where yung Gauss's law mo, saan napadali yung buhay natin. And then, from the del cross E, the curl of E is 0. May napala din tayo dito kasi pag ginamit mo yung Stokes theorem dito, makukuha mo na yung closed integral ng E dotted with dl equals to 0. And from this, nabuo natin yung electric potential formulation. Okay, nabuo natin dito yung electric potential. So yung V will be V dot dl. Okay? So nabuo natin yung electric potential dyan, which is nice. And yung potential na ito, napadali lalo yung buhay natin when it comes to calculating electric field. Okay? So sa magnetostatics, kinuha rin natin yung divergence and curl. Tapos nakuha natin na yung divergence is 0. The curl gives us something. Okay. Then it should have something na dapat may ibibigay pa tong extra sa atin. I mean, itong part na ito at least. Okay, kasi dito sa part na to, both sila nagbigay ng something for us. Okay? This guy, ito yung kanina, nakuha natin na yung B.dl is just equal to mu naught I enclosed. Okay? Which is nice, which is very easy to use. Alright. Now look at this. Yung divergence nag-exist for electric fields. And you know that the electric field diverges from charges, di ba? Meron kang positive charge plus Q. And you know that the electric field lines go outward. Okay? Amazing. And then you know that, tapos dito naman sa magnetostatics, nalaman natin that the magnetic field curls around your currents. So when you have a current, yes, very straight. Yan. Current, you know that by the right hand rule, nag-rotate nag-curl yung magnetic field mo. Okay? Which is nice, diba? Very elegant yung mga bagay-bagay. Kasi there is symmetry between them. Okay? Alright. Noong unang panahon, sila Coulomb, akala nila yung magnetic field ay due to magnetic charges. Magnetic charges. Or in our modern day term, ito ay magnetic monopoles. Kung alam niyo siya. Which does not exist. Okay, which does not exist, at least for now. Hindi pa natin alam kung talaga mag-exist ba siya or not. Okay, so yung magnetic monopoles, it does not exist because of this guy. Okay? So in del dot B is equal to 0. So what does this entail? Tingnan natin na kasi when you pag yung divergence mo kasi 0, ibig sabihin all the field lines that's coming in is also coming out. Parang baliktad na. All the field lines that is going out also comes in. So kung maalala niyo yung magnets niyo, it's, di ba alam natin na yung field nito pa ganun. Parang sa mga science experiment natin ng kids tayo, na pag nilagay mo yung iron filings, makikita mo that the magnetic field lines goes like this. And whenever you try to break this down as a smaller pieces, makukuha mo na yung smaller pieces, meron pa rin north and south, meron pa rin north and south. So you can't continuously break this down, di ba? Makakabuo ka lang din ng magnets. So in essence, this guy, whenever you try to enclose this with an area, lahat ng lalabas, papasok din mamaya. Okay? So lahat ng lumalabas, papasok din sa kanya. Kaya siya walang Gauss's law na essence. Sa mga charges mo kasi, pag in-enclose mo to, you're sure that every field line goes out and never comes back. Okay? Okay. And makapansin niya, it's nice na, kuwari dipole pinili mo. Dipole. Kung naalala niyo pa, that is plus 2. And then, minus q. Sige, gawin na lang din natin right. Right. Minus q. Tapos yung field lines natin, i-drawing natin. Tingnan nyo to. Di ba kamukha niya yung field ng ano? Kamukha na yung field na to. Amazing, di ba? Kamukha sila ng field, di ba? May pinapasukan na point, tapos may nilalabasan na point. Okay? So, ito yung nabaliktad ko lang yung drawing. So, in essence, pag kinuha mo yung Gauss's law nito, 0, di ba? Kasi Q enclosed mo would be plus Q and minus Q. So, anong Q total mo ng 0? So, nawawala din yung Gauss's law dito pag ganyan yung field. Okay, so may tanong sa atin. Sir, may tanong po ako. Dun sa B.dl po ng Ampere's law, need lang po ba na parallel yung Amperian loop sa magnetic field? Kailangan rin po ba na same direction? For example po, pwede ka po bang gumawa ng Amperian loop where in one section nagra-run in the same direction, in B while the other how do you propose to do this? So, ang point niya is paano raw okay, yung magnetic field mo naturally comes in loops. Okay, you can't have something na I don't quite understand the question. I'm so sorry. So, okay. So, kuwari, kumuha ko ng isang Amperian loop. Let's try to imagine this. Let's say, kumuha ko ng loop, the square loop. Okay. Okay. And then, And then, magnetic field ko is downward. Suppose na yung magnetic field natin is all downward. Ganyan ba yung nasa isip mo? Kasi parallel siya with this side ng Amperian loop mo. Parallel siya dito sa side na to, tapos dito anti-parallel siya. Ayun ba yung tanong mo? Sorry. Okay, ganito. Pag ganito, sige, try mo. Wala kang makukuha current sa loob. Wala kang makukuha. So, yung ano dito is, kuwari, say, gawa tayo ng coordinate system. This is A, B, A, B, and this is length L. Okay? So what happens here if you try to do this is that, syempre, iba yung, okay, yung positive yung B, okay? Tama, kasi B, tama. Kasi yung B.dl yung prescription mo. So kapag sabay sila, sabay yung loop at direction ng magnetic field mo, positive dapat. So yung direction ng magnetic field ko at B is downward, then the loop here at B is also downward, so therefore it is positive. Then for B, A, anti-parallel silang dalawa, so that's negative. Then I multiply that with how long? That's L. And then, what do I enclose? 0. Kasi walang current inside here. Okay? So this tells me that yung mga field lines ko would always be equal. Would always be equal. So this tells me that itong mga linyang to, equal lang sila. Does that answer your question? So, yes, in essence, dapat hindi mo papahirapan sarili mo. Dapat parehas yung loop mo dun sa direction ng magnetic field. Okay? And then magiging valuable siya if may ma-enclose kang current. Okay? Okay. Alright. So now going back, amazing kasi may symmetry yung magnetostatics mo and electrostatics. Now, we continue and find out what's happening in del dot B is equal to 0. Okay. Okay, with this guy, okay, so yung del cross E, ang na-produce natin is yung potential mo, which tells us that E can always be expressed as a gradient of the potential. Okay? And now, kapag dito, sa divergence ng magnetic field, if this is 0, then you can always find a magnetic field that is equal to the curl of some magnetic vector potential A. Okay? So, kung sa E, last time, may nabuo ka na E is equal to negative gradient of some potential V. This time, meron kang ganitong relationship. Okay? So, whenever you find A, you can get the curl of that to produce B. Parang hirap, sir. Parang lalong naging komplikado. Yes, naging komplikado lang. Okay. Let's find out the Ampere's law. Ampere's law, kunin mo yung curl ng B, di ba? Dapat mu naught J siya. So, kapag kinuha mo yung curl ng B, dapat makuha mo si mu naught J. Okay? And then, the curl of B entails us that if we're gonna do that, plug in natin tong ina-assume natin na value ng B. Okay? So, curl ng A. So, triple product, nandito yun sa first chapter, that would be equal to this guy. Okay? That would be equal to this guy. All right. Now, we have the freedom to choose which we want to zero out. Okay? Apparently, mas madali i-survive to second term. Diba? Kasi Laplacian to. And na-solve na natin yung Laplace equation last time. Diba? Madali lang mag-solve ng Laplace equations last time. Okay. So, in essence, we want to take the divergence of A, the magnetic vector potential, to be zero. Okay? Gusto natin siya mag-zero para mas mapadali buhay natin. Okay. Okay. Does the divergence of, can we prove this to be zero? Okay, yes, we can prove this to be zero, but in the end, ikaw pa rin yung pipili. Ikaw pa rin yung pipili ng kung paano siya magpapa-zero out. Okay? So, kuwari, sige, sabihin natin yung, kumuha tayo ng some A0 na non-zero. Okay? Non-zero siya. Okay. And suppose dagdagan natin siya ng value. Let's take that to be nakopya ko lang yung notes ko. Let's take that to be kuha tayo ng some gradient of some function lambda. Okay? And then, suppose this is our new A. Okay? Okay? So, bakit natin ito ginagawa? Tingnan lang natin. Tingnan natin magagawa. So, kuwari nakahanap tayo ng A0 na hindi zero yung divergence niya. Okay, so, ngayon, try natin dagdagan yung A0 na yun by some divergence of lambda. And then, we can add anything. No? We can add anything. Mas madali lang to gamitin para mamaya makikita nyo. Okay? So, if we take the divergence of A, that would mean that we're getting the divergence of A0 and then plus the divergence of this guy, which is the Laplacian of it. Okay. Kaya ko siya sinulat as gradient para maging Laplacian siya. Okay. Then, sabi nga natin, gusto natin maging zero ito. So, to do that, dapat, sige, equal natin sa zero ito. Then, we should say that yung i-propose natin na idadagdag natin, which is yung second term, this guy, would actually match the value of the yung divergence na hindi zero. Kasi hindi to zero, di ba? So ngayon, we're free to actually add this guy. And we know this guy. We know how to solve things like this. Okay? We know how to solve that. Okay? So ito ay Laplace equation lang. Okay? So we know this. So yeah, you can actually add something to your A to make it always zero. Okay? Ayun lang ang point ng derivation na to. Can always add something. Kaya lang tayo nag-add ng divergence ng gradient ng something, gradient ng lambda. Is para pag kinuha natin yung divergence niya, maging Laplacian lang siya. Pero in fact, you can always add something A0 or some constant or whatever. Basta ang mahalaga lang is ma-produce mo yung curl ng A that would actually be zero. Okay? So, anong similarity nito sa potential? Kung naaalala nyo sa potential, you can always add something to your potential. Ang essence ng pinagsasabi ko, yung sa electric field natin, sa electric potential, you can always add something here, di ba? Pwede ka mag-add ng constant and you would always actually have your electric field the same thing. So kung wari, yung potential mo is 2x, then the electric field is kunin mo yung negative gradient ng 2x, so that gives me 2x hat. Tama? Okay, so I can always add whatever constant I want here. Okay, so I can add 1,000 and you'd still have your electric field. Okay, so in essence, ganun lang din yung essence dito. Now you can add something to your vector potential A. Okay? Okay, so we have this. Okay? So again, pwede natin zero out to. Pwede natin to zero out. But that would complicate things. Okay? We can always say that this zeroes out and this one survives. Okay? Pero, pag natin pahirapan sarili natin, solve natin itong bagay na to. Okay. With this, we have the Laplace equation. Now, the solution for this, gagawin nyo yung Green's function, di ba? Naalala niyo pa ba yung Green's function? Okay, kung hindi, okay lang. So, pero ang lalabas lang dyan would be, this is your magnetic vector potential. Now, it's not as useful as yung electric potential mo kasi kung makikita mo dito, yung pag-calculate ng A is still using a vector J, the current. Okay? So may direction pa rin. Kasi electric potential kasi nawala yung direction, di ba? Yung scalar function lang siya. Kaya siya madali. Pero ito ay useful pa rin naman kasi nawala yung cross product mo. Okay? Minsan kasi nakakalito yung cross product, di ba? Nakatwist siya ng utak mo kung paano mo siya gagawin. Okay? So this guy tells us that yung A mo, yung vector potential is parallel to your J. Okay? Okay? So sa B kasi last time, this guy is I cross R hat. Diba? So perpendicular siya sa dalawang to. Which is not very intuitive. Dito intuitive kasi kung ano yung direction ng current, ayun yung direction ayun din yung direction ng vector potential mo. Sir, may geometric po ba na significance for magnetic vector potential? Wala pa siyang significance for now. Okay. Mathematical, ngayon mathematical object pa lang siya na tutulong sa pag-solve. Pero sa chapter 10, dun pa lang siya nagkakaroon ng use. Pero yes, meron siyang significance in our physical problems. Yung magnetic vector potential. Okay? So, paano siya ini-imagine? Imaginein mo lang na meron kang potential that is hirap nga pala imagine nito. That goes along with your current. So sabihin natin na yung meron kang kunyari na current I. Okay? So you know that A would actually be parallel with your I. Okay? That's your A. Okay? So that is your A. And you know na yung A mo nagde-decrease siya as you go far from the source charges. So just humihina siya. So kuwari this is actually weaker. Okay, kuwari mas weaker pag mas maliit yung flow. Okay? Okay? Alright. Then, ayan yung ano mo, ayan yung magnetic vector potential mo. Which basically tells you that whenever A is strong, malakas din dun yung magnetic field mo. And yung magnetic field mo is actually around here. Malakas siya sa loob. Kasi dun concentrated yung A. Okay. And then humihina siya as you go far. Okay. So, ganun lang siya. Ganun ko siya ina-imagine, no? You can always have your way in imagining things. Okay? Alright, that is your magnetic vector potential. Now, wala pa tayo example. Gawin natin sa Tuesday para fresh, para ready for exam. Okay? Okay. So now, syempre, meron tayong boundary conditions to check kung ano tama ba yung pinaggagawa natin yung left. Okay. Let's prove this, guys. Kuwari, ang boundary condition, again, would be surface dependent. So whenever you have some surface na merong surface current K, then what happens? Gamitin natin yung mga gamitin natin yung mga facts natin. Del dot B is equal to 0. Okay? Del dot B equal to 0. What does this gives us? So, del, parang Gauss's law to, di ba? Pero B dot dA must be equal to 0. Okay, kuwari gagawa tayo ng Gaussian pillbox. Kasi this is, kuwari, isipin mo lang to as magnet electric field. Okay, kuwari ayun yung pillbox mo. Okay, so meron kang dalawang area above and sa taas. So lahat ng field, kuwari lahat ng pataas na magnetic field, what color can we use? So, B below, all that is perpendicular, below lang nagawa ko, B below. Okay? So, lahat ng perpendicular sa surface na area mo, tapos, kunin mo rin yung nasa taas, B above, that is perpendicular. Okay? So, we do this, you know that, okay, given agad na 0 yung right-hand side. So, BA, okay? BA, kasi alam na natin na perpendicular itong dalawang to. So, B times yung area ng pillbox, that's 2A. And then, you know that hindi natin alam kung ano yung difference ng dalawa. So, B above minus B below. Kakalito. Okay, bakit minus yung B below? Kasi yung area vector mo, pababa dun sa part na yun. Okay? So, 2A pa rin. And it just equal to 0. Then this tells me that B above is always equal to B that is perpendicular below. Okay? Pan-check tong mga bagay nito. Okay, then how do we do this? Side view tayo. Kuwari ito yung sheet mo. Yung sheet of current. Oh my God. Sheet of current. Then, of course, papunta sa atin yung papunta sa atin yung current. Okay? Yan, ito yung direction ng current. So, ibig sabihin nito ay out of the page. Tapos, X ay into. Tapos ito ay out. Okay? Alright, kuwari papunta sa atin yung by the right hand rule, alam natin na yung taas would be this guy. Kanina dinrawing din natin to. Ito yung magnetic fields on the upper and lower parts. Okay, so we make a loop. Very straightforward naman. Gagawa tayo ng Amperian loop para makuha this guy. So that's B.dl. dl closed, and that would be mu naught I enclosed. So the mu naught enclosed will be K times yung L. Okay? Kung gaano kahaba itong gagawin nating loop. Okay? Okay. Ayun lang din yung kanina, di ba? Tapos, yung B mo would be two things. So, yung okay, so denote natin na above ay B above parallel. Ito yun, this guy. And then B below parallel times kung ano yung length, that would be L times L. Okay, tama ba? Kuha. Bakit natin hiniwalay yung dalawang L? Kasi? Bakit nga ba? Ay, okay. So, mali pala ako na nag-drawing, guys. Try natin to. Well, tama naman, pero it's not very intuitive. Okay? Denote natin na yung field na pa ganito at field. Kasi last dito sa definition natin kanina, nag-drawing tayo ng nag-denote tayo ng B above would be this vector and B below would be this vector. Okay? So, dapat similar lang din yung gagawin natin for this case. So, let's say that this is B above and this is, this guy is B below. Okay? Tingnan natin yung discontinuity between them. Okay? Okay. Let's go back. Okay, let's do this. Okay, sa B above, negative. Then, this is that. Then, sa below would be this guy. Okay? And then, that's your magnetic fields. Mumultiplyan mo siya ngayon ng length L. Of course, para makuha lang yung parts na kailangan mo. Okay? Though, cancel lang yung L mo. So, in essence, yung discontinuity between the discontinuity between them would be negative B above plus B below. Okay? And that's mu naught K. Okay. Okay. So, ang assumption dito, baka maguluhan kayo sa pagtingin nyo mamaya sa libro nyo, is yung K is into us, papunta sa atin yung K. Ay, out of the page, bale. So, in essence, kapag binaliktad mo, pag into the page yung gagawin mo, pag into the page, ang magiging katumbas niyan would be B above minus B below. Mu not K. Okay, so si K dito is intrinsically negative. Kasi hindi na nakalagay dito that is out of the page siya. Okay? Okay, wag kayo malito. Basta ang mahalaga is yung difference nila would actually amount to mu not K. Okay? So, mas madaling sundin ito. Mas madaling sundin yung ito. Para ina-assume na positive yung K. Okay, dito negative yung K dito. Alright? Okay, so in general, you can have it in a vector form, and that would give me this. Okay, B above minus B below is equal to mu naught K cross n hat. Okay? So, kung yung K mo is towards, kuwari, x hat ito, x hat, tapos yung field mo, ay yung ito pala yung current mo, tapos yung, bakit pala na? Bakit na x? Bakit ganun? Piliin na lang natin ibang coordinate. This is y, kuwari towards y, direction yung, so, in this case, this is y hat, and this is x hat, and then yung vertical component would be z. Ayan. So, cross y cross z. Okay, try lang natin. Yung b above, b below. Oh my god. Y cross z. What's that? Mu not. May k ka pa dito. K, y. Okay. Mu not k x. Okay? So what does that give me? So x hat direction yung makukuha mo, which is this guy. Okay? Nalabuan ba? Nalabuan? Okay? So that assumes na nasa taas ako, above ako ng ano. Kasi na z, positive z, kinuha ko. Pero pag negative, magne-negative sign to, so bababa yung current. Bababa yung magnetic field. Magre-reverse ng direction. Okay? Okay, and then if you are going to use that in your magnetic vector potential, these boundary conditions occur. So, straightforward yung derivations nila dito. Okay, so dapat continuous. Like the potential, the electric potential, dapat continuous yung magnetic vector potential. And this is nice. Tingnan nyo ito. This is nice. Ang A dotted with DL is, kung gamitan natin siya ng Stokes theorem, this would actually give me equal to del cross A dA. Okay? And del cross A, we know del cross A is just D. May dotted with dA. Which is nice, no? Ito ay parang Ampere's law. Ampere's law for your magnetic vector potential. Or of course, you can always use the flux. Kasi madali imagine yung flux. Ito mahirap imagine. Okay? And then consequence nitong thing na to is this guy. Okay? Kapag in-evaluate mo yung del plus A, makukuha mo ito. Alright. So that's your boundary conditions na pwede nyo gamitin to check your answers. Okay, and then lastly, the multiple expansion for the vector potential. From last time, yung multiple expansion natin na lesson, nasaan yun? I think that's lesson 12. Here we go. Alright. Ayan, nakuha na natin to. That 1 over r is this. And then we have written this as the Lagrange polynomial, which is t. Okay, so we know that 1 over r is this guy. Okay? The 1 over curly r. So we exploit that result. And this is that. Tapos plug in lang natin siya ngayon dun sa magnetic sa magnetic vector potential mo. Vector potential insert. Okay. So ayan, plug in lang natin yung 1 over r, and then we find that we have this guy. Okay? Okay, ba't nag-close loop doon? Kasi nasa DL fast ka. Okay? But if you're going to solve this for the volume current, you'd have to switch, okay, such that ma-enclose mo yung current. Okay. Pero minsan kasi hindi mo ma-enclose yung current pag infinity yung current mo. So you'd have to resort to using this. Okay? Okay, so we have this guy, which is just the same as before. Parang umulit lang, di ba? Okay, but this time, yung direction nito would be the direction of your current. Okay, let's try to look at some values of this. Kapag n is equal to 0, kung naalala nyo, n is equal to 0, that would be your monopole term. Kung naalala nyo sa potential formulation natin, yung multiple expansion din doon. Di ba nagkaroon tayo ng dipole term, monopole term, etc. So n is equal to 0. We try to find that. 4 pi, and then 1 over r. Tapos, this is r prime raised to 0, which is 1. Tapos, p0 is just 1, dl prime. Okay? So, what is the closed integral of dl prime? 0. Diba? 0 lang yung closed integral ng line. Kasi, babalik ka sa starting point mo. Okay? So, that's 0. We have this. That's it. So, we know that the A monopole term is 0. Okay? So, parang wala talaga theoretically yung monopole na charge, magnetic charge mo, no? Okay? So, nagsistart yung the greatest contribution would start from the dipole contribution. Okay? So, when we plug in the dipole contribution here, so lagay mo lang n is equal to 1. So, magiging r prime tapos p1, which is just cosine alpha. We have this. And then alpha, of course, would be the angle between your r prime and your r. Okay? So, the angle between r and r prime. Okay? So, pag dinot product mo, ito ilalabas. Okay? Convinced ba? Convinced? Okay, so and then we can actually find this in your chapter 1 sa mga integral rules ata to. Okay. So, from here, you can write this guy. Okay. Okay, and then switch natin ng position. Pag nag-switch tayo ng position, mag-i-induce ka ng negative. So, equal lang din to sa cross r hat. Okay? Okay, and then let's write this down as M. M. Hindi N. M vector. Okay? And then yung M vector, let's call that the magnetic dipole moment. Magnetic dipole moment. Okay? Magnetic dipole moment. Alright. Okay. So, dipole moment. So, right. Actually, ang dipole moment ay may kasama pa siyang I. Okay. So, ang M pala ay equal to, M is equal to I dA. Okay? Ano lang, then notation lang. Okay. So, in essence, this is actually IA. Kung makukuha mo yung... So, hindi sila dot product, no? There's no need to get the dot product between them. Okay? So, basically, you have a magnetic moment whenever you have a loop. Yung loop mo, may current ka na flowing through that loop. Tapos, yung area mo would be the area of this guy. That would be your A. So, may magnetic moment dahil yung mga gantong setup. Okay? So, whenever, let's try to position M. So, let M be, okay, sa Z hat direction siya. So, let's try to draw this. So, hindi na pala natin draw kasi nandito na siya. Okay? So, whenever you have Z hat na direction, that would mean that your area is actually on the XY plane. Tama ba? Kasi magkakaroon ka lang ng ganon na Z component kapag yung area mo is actually lying down on the XY plane. Okay? So my point is that whenever you have a loop in the XY plane, it produces this magnetic vector potential. Okay? Okay? And then, of course, if you get the curl of this guy, mapuproduce mo yung magnetic field. Okay? So that is your curl, and this would produce this guy. Okay, kamukhang-kamukha niya yung, ito rin yung equation ng dipole, electric dipole. Pagpunta natin. Lesson 12. The field of a dipole, okay, and 2 cosine theta, sine theta. 2 cosine theta, sine theta. Tapos r hat, theta hat. 2 cosine theta, sine theta. Ang galing, di ba? Parehas sila ng itsura. Okay? Amazing. Parehas sila ng itsura. So, anong itsura niyan? Ganito itsura niyan. Okay, kamukhang-kamukha nung ang pinagkaiba lang nila, kung maaalala niyo yung sa dipole, tingnan natin. Ganito yung positioning ng dalawang charges. Nasa z-axis sila parehas. Tapos dito, nasa xy plane na yung loop mo, yung current loop mo. Okay? So amazingly, no, if we imagine the Earth, okay, wala yung Earth. So axis. Okay, gawin lang natin ito para mukha siyang globe. Okay? Tapos, may nakasprinkle dyan na charges tayo. and some other materials. And it rotates. And it rotates. Okay, it rotates. So, yung charges mo nagro-rotate para kang may surface current. May surface current ka na umiikot sa earth mo. Okay, so we imagine that kung pa-plot lang natin yung current. Yung current. Okay. Kuwari nasa loob yung earth mo. Kuwari spherical niya. Okay. Tapos, ito yung axis mo. Okay? So kapag ganyan yung current mo, paano yung magnetic field mo? That would be, of course, circling out. Amazing. Nagsi-circle out siya, di ba? Para siyang dipole. Okay? Para siyang collection ng dipoles. Kaya tayo may magnetic field na ganyan yung itsura. Okay? So, imagine niyo na lang na continuous siya. Ayan, amazing, di ba? Okay. Ayan. So, ayan siya. So, may nagra-radiate outward or yan. Kaya pag gumamit tayo ng compass, tumututok siya, nag-align siya sa magnetic field ng Earth. Kasi yung surface ng Earth natin, lalo na sa clouds, yung mga electrical charges dyan, na pag umiikot sila, nagiging surface current na sila ngayon. Okay, amazing, di ba? Okay, so that's it for now. Ayan yung mga bagay na... So, yung example natin, gawin natin sa Tuesday. So, magnetic vector potential, kung paano ba yan ginagawa. Okay? And then, may mga tanong ba? Saan naguluhan? Feeling ko medyo magulo yung discussion ko dito sa part na ito. But you can always try to read it sa Griffiths. Tingnan nyo kung paano nyo siya mag-gets in your own way. No? And if not talaga, you can always message me sa Canvas para mapalinaw natin kung mga ganitong bagay. Okay? So, try natin to sa Tuesday, no? Magpo-post ako ng prob set mamaya. So, may prob set kayo, sa Tuesday na isa sa Meet. Okay? Tapos, next week, tatry natin na i-solve yung first exam. Pakita natin yung results para din malaman nyo kung ano yung mga tamang ginawa nyo or mga mali nyo ginawa. Okay. So, any questions, any clarifications regarding the topic today? Wala naman. Okay. So, wala nang tanong. So, basically, tapos na tayo sa chapter 5. Ano next na natin na topic? Magnetic fields in matter. Okay? Parang electric field lang din, di ba? Sa electric field, kumuha tayo ng hard way, yung Coulomb's law, tapos Gauss's law para madali, then potential para dumalo. Sa magnetic fields, magnetostatics, ganun din. Kaso, napansin natin sa magnetic vector potential, parang hindi siya ganun ka-helpful, no? So, sir, yung prob set po ba na ibibigay niyo for chapter 5, kailan due? Iniisip ko Tuesday, next meeting, kasabay na rin nung naulang prob set. Para ma-practice nyo na siya bago mag-exam. Kaya ba? Dalawang questions lang din. Parang, yung binigay ko nung last time, di ba? 2 questions lang. For chapter 4. Chapter 5, 2 questions na yun. Mag-curate pa ako ng questions para hindi naman heavy. Para din, makapag-aral kayo sa 140 niya. Kaya, wag na Friday yung Para full focus mo kayo sa Friday night niya. Gano'n ba katagal yung exam niya sa, sa 140? Yes. Gano'n katagal yung 2 hours. Okay. Good luck. 2 hours lang pala yung exam niyo. Oh my God. So scary. So, same thing. 12 hours pa rin yung exam natin. Para mapag-iisipan nyo yung mapag-iisipan nyo yung questions. Okay. So, personally daw, hindi daw kaya yung dalawang prob set. Pero ano na to yung nauna kong binigay, Tuesday na yung Tuesday na talaga yung deadline. So, pinag-iisipan ko lang ibibigay ko ngayon kung Tuesday or Friday ba yung deadline. Pero sige, kung hindi kaya, edi Friday na lang. Okay. Gusto nyo ba Saturday din yung So, pag-usapan nyo yung pag-usapan nyo yung kung kailan nyo gusto yung exam. Yung kung November 17 ba before your 140 or November 20 after your 140. Kasi 12 hours naman yung exam nyo 12 hours naman yung exam mo. Kaya naman siya. Not as tedious as 2 hours na speed run. Pabilisan. Hirap yan 2 hours. So anyway, so pag-usapan nyo ngayon, kayo mag-block. Then message nyo ako sa Canvas. Kahit ako na lang message nyo kung anong gusto nyo. Tapos ako na magsasabi kay Sir Bagun. Okay, so sana this weekend mapag-usapan nyo kung kailan nyo gusto. Okay ba? Okay ba yan? Thumbs up, thumbs down? Okay. So pag-usapan nyo. Okay. Flexible naman kami ni Sir Bagun. Alright, so sige. Stop.